Okay. Welcome everyone to lecture number 21. Our topic today is infinite series. And just to recap, in the last couple of lectures, we've been talking about sequences and about the concept of convergence for sequences. So today we're going to develop that to a slightly different idea, which is that of an infinite series, which is something that I suppose is related to sequences, but has maybe more obvious kind of practical uses. So today our plan is to have a look at the concept and meaning of an infinite series and to identify some examples of what it means for an infinite series to be convergent, and to have a look at a few examples and a few cases where we can do some extra analysis. Okay, so today at our second last lecture of kind of new content as such, we'll have one final topic next Wednesday, which will be about representation of functions using these ideas about infinite series and convergence. And then our last lecture next Thursday will be for review and for a look at the I suppose a preview about the exam and a look at some exam type questions. So if anybody has anything that they'd like to include in next Thursday's lecture in that review, or indeed in anything else that might be accompanying it by way of online materials, please just let me know and to get in touch by email during the week if there's anything in particular that you'd like to make sure it gets mentioned next Thursday. If not, I'll have some general advice about what to expect in the exam and about how to go about answering questions in an exam type environment. Okay. That's where we are. So section 3.3. So a series or an infinite series basically is the sum of all the terms in a sequence. So when you look at a series, you're not just talking about a list of terms, you're talking about trying to somehow add up all those terms. So here are a couple of examples. So there are two things here. One is the concept of an infinite series, and the other one is the notation that accompanies it. So if we look at 1 plus 2 plus 3 plus 4, kind of imagining the sum of all the natural numbers starting with 1, 2, 3 in their usual order, that's an example of an infinite series. Okay, so I'm not saying that this thing is a number. I'm not saying that it's an addition task that we can do. I'm saying that this is what we would call an infinite series. Okay, so at this point, it's sort of a formal definition. And this thing would be written in this form, this sigma, this capital letter sigma, it's used for sum. And this is saying that we're taking the sum of the expression n as n goes from 1 to infinity, and although it's not stated there, it's implicitly meant that n runs through the natural numbers from 1 to infinity, so it takes integer steps. So that means 1 plus 2 plus 3 plus 4, and so on. It continues through all the natural numbers. Okay, so that's an example of an infinite series. I'm not saying that we can do anything with it, or that we can that it has any particular meaning as it's written there, but that's what a series looks like. Okay, an example of a series that's called geometric is this one. So in this case, the nth term is 1 over 2 to the n. N goes from 0 to infinity through all the natural numbers again. So when n is 0, we get 1 over 2 to the 0. That's 1. That's the first term. When n is 1, we get 1 over 2 to the 1. That's 1/2. That's the second term. When n is 2, we get 1 over 2 squared, and so on. So this is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. And again, the fact that we're starting at 1 and continuing is written here at the point that we're starting with n equals 0 and continuing through all the natural numbers as the values of n. Okay, and the fact that we have this sigma symbol here tells us that what we're talking about is a sum, not just a list of those terms, which would be a sequence. Okay, so the second one there, I guess the first one, okay, I mean, you can quickly see that if you start adding 1 plus 2 plus 3 plus 4 plus 5 and just keep going, your sort of running total just grows without bound. It flies off to infinity. If you take 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, but there it's less clear, because at least you can say that what you're adding on at each step is shrinking towards 0. So maybe maybe there's something more that you can say in that case about the behavior of this sum as you continue adding more terms to it. And that's really what we'll be concerned with today. And the other remark is that in that second example, every term, so the terms of the series are the individual pieces of the sum there, the terms 1 over 2 to the n. So the word term is used in series in a similar way to how it's used for sequences. And each term there is obtained from the previous one by multiplying by 1/2, which is referred to as the common ratio for this geometric series. And that's what the word geometric means. In a geometric series, it means that each term is obtained from the previous one by multiplying by a fixed number, which doesn't change throughout the length of the series. Okay, so basically, a geometric series is one in which there's a common ratio, some fixed number, and each term is obtained from the previous one by multiplying by this fixed common ratio. Okay, and geometric series amongst the whole universe of infinite series are amongst the friendlier ones and the easier ones to manage, as we will see in a few minutes. Okay, so that's that's a couple of examples of infinite series. A couple more examples. We saw this one before, but we haven't really done a lot of analysis with it yet. We will today. The harmonic series is a particularly special example. And this is the sum of the reciprocals of all the natural numbers. So sum of 1 over n as n goes from 1 to infinity. So 1 plus a half plus a third plus a quarter plus a fifth, and so on. It's an example of an infinite series. And we'll revisit that one a bit later today. And there's a final example. This is an example of what they call an alternating series, because the signs of the terms are alternating positive and negative as we travel through. And it's just the alternating series whose terms are minus 1 to the n as n goes from 0 onward. So the n equals 0 term is minus 1 to the 0, which is 1. The n equals 1 term is minus 1 to the 1, which is minus 1. The n equals 2 term is minus 1 squared, which is 1, and so on. So the terms in that series just alternate between plus and minus 1. And of course, if you imagine this as a sort of addition exercise, which is not one that we can do because it has an infinite amount of steps, but if you start it, you get 1 minus 1 plus 1 minus 1 plus 1 minus 1. So of course, you can observe that your running total, if you try to add together the terms of this series from left to right, just alternates between 0 and 1. Okay, so we'll have a look at all these things and see the different sorts of behaviors that can arise. And also, hopefully, before too long, we'll see some practical reasons for being interested in these infinite series. Okay, anybody have a comment or a question at this point? Okay, well, if not then, okay, so I suppose what I hope you'll have sort of taken from this so far is just the meaning of the term infinite series, that it's a sum of infinitely many terms, typically indexed by the natural numbers or by some sequence or some indices that resemble the natural numbers. Okay, so for the moment, these infinite sums, you know, they're just formal expressions or arrangements of symbols. So, you know, if you write down like in our first example, you know, the sum of all the natural numbers from 1 to infinity. That's 1 plus 2 plus 3 plus 4, etc. So, you know, that you can write that down. You can write anything down. It doesn't mean that it has some kind of numerical or conceptual meaning, even. So, yes, that's what I mean by saying it's just a formal expression or an arrangement of symbols. Of course, you can write down a bunch of things and put plus signs between them. That's kind of what we have so far. So, what we really want to investigate is whether it's meaningful to think about something like that as a number, whether we can meaningfully attach a numerical value to the sum of infinitely many things. Okay, and the answer, of course, as usual, is sometimes you can, and sometimes you can't. We'll try to sort of get at how to decide that, or at least how to conceptualize it. Okay, second remark. This is an important one. Just as usual in calculus, there are lots of different words floating around in our vocabulary, and it's important to not to confuse them. So a series is not the same thing as a sequence, even though the two words are, you know, sort of similar uses. So try not to confuse these expressions, the words sequence and the word series. So a sequence is just a list of numbers, typically separated by commas. A sequence in particular doesn't come with any arithmetic operation. It's just a list of numbers. But a series is an infinite sum. So a series is an infinite sum, a sum of infinitely many terms, which might belong to a sequence. Okay, so that's the distinction between a sequence and a series. It's hard to remember which is which. I guess you have to sort of remind yourself until you're no longer at risk of confusing them. But it is easy to confuse them, and it's certainly helpful if we can avoid that. Okay, a remark: the sigma notation, in case anyone's not familiar with it, the sigma is a letter from the Greek alphabet, and an uppercase sigma is a symbol that's used for sums. The lowercase sigma is this thing which we also met, and you've probably met it also with Dane talking about permutations. This is a letter from the Greek alphabet, and the uppercase sigma is used to denote sums. So basically, if you write down something like this, sum of an, and if you've got some decorations as subscripts and superscripts on the sum part, that basically tells you where you're starting and where you're finishing. Sometimes you don't need to write those if it's completely clear from the context, but often it isn't. So this means we're taking an expression an, it's got a value for natural numbers n, let's say, and we're taking the terms ai plus 1 up as far as aj, and we're adding them together. So that's what this expression means. And for infinite sums, you can have infinity or minus infinity as a superscript or a subscript on the sum symbol. And then it's usually, even though it doesn't sort of say what the increment is, it's typically assumed unless stated otherwise that you're summing. If it says n equals 0 to infinity, for instance, of an, it's taken as read that the increments are just consecutive natural numbers. So if you have something like that, this means a0 plus a1 plus a2. Obviously, there's no a infinity, but it just means we add up in our series all the terms for all the natural numbers. Okay, so we can have infinity or minus infinity instead of fixed starting and end points as the in this machinery for denoting sums. Okay, so I suppose it's useful to get used to this notation and get used to using it, both writing it and reading it. You know, one can sort of get by and lots of examples of sort of writing out a few terms and putting dots between them or whatever. But this compact notation, as often in mathematics, is something that's very useful once you get fluent with it and very convenient to be able to use it. Okay, so that's a bit of general kind of remarks, I suppose, about series. What are we actually going to do? How does this relate to the work that we've done in the last couple of lectures about sequences? Well, okay, so really our question, I suppose, is if somebody hands you one of these infinite series, you know, so they're handing you a sum of infinitely many numbers. We can add up finitely many numbers, no problem. We can do it in practice if there's relatively few of them, and we can do it in principle, no matter how many of them there are. So, you know, we understand finite sums of numbers. And the question really here is, can it ever make sense to add up an infinite collection of numbers? And can the sum of that thing ever itself be a number? And to answer that question, we have certain machinery, I suppose, at our disposal. We have a theory about sequences that we've developed in the last couple of lectures. We know what it means for a sequence to be convergent in particular. And so in the examples that we looked at, so all of them have the same basic form, infinite sum of some terms. And we know what the terms are, maybe. And so, yeah, you've got a first term, a second term, a third term. You can start at the beginning, you can start adding them together. And so if you take, for example, the first example that we looked at, the sum of all the natural numbers, 1 plus 2 plus 3, and so on. So you can sort of look at that thinking, okay, this is not going to be a fruitful exercise if you persist with it too long, but you can think of it as basically being an addition exercise, which starts with 1 plus 2 plus 3. And if you stop after the first step, you've stopped at 1. So 1 is kind of like this, you know, if you just give up on the addition after the first step, you have 1. If you do the first 2 steps, you've got 1 plus 2, which is obviously 3. If you do the first 3 steps, you've got 1 plus 2 plus 3, and that's 6. If you do the first 4 steps, you get 10. The first 5 steps, you get 15, and so on. And so basically, given any series like this, you can do this trick, or you can imagine doing it. You know, you can add up, you can take just the first term. You can take the sum of the first 2 terms. You can take the sum of the first 3. You can take the sum of the first 4, the first 5, the first 6, and so on. And you can continue doing this until you get bored of it. And you can write down these partial sums. Okay. So, and in this particular instance, where our series has terms 1, 2, 3, 4, etc., the first partial sum, which consists of the first term only, is 1. The second partial sum is 1 plus 2, that's 3. The third one is 6, 1 plus 2 plus 3, and so on. So associated to any series, you have a sequence of partial sums. That's a sequence, it's just a list of terms. And the kth term in the sequence of partial sums is the sum of the first k terms in the series. Okay, and the point here is not that we actually want to write down all the terms of the sequence, it's that, you know, associated to every infinite sum, you have this sequence of partial sums. And we know something about sequences. We have some theoretical and conceptual machinery for dealing with them and for considering when they are convergent and so on. In this particular instance, and again, you know, this is not a surprise for this particular series. You know, these partial sums are growing, and the gaps between them are growing as well as we travel further out. The next one's going to be 21, then 28, and so on. So they're growing quickly. They're not going to. They're going to continue growing without bound because what we're adding on at each step is increasing all the time. Okay, so that's fair enough. These numbers in our list that starts 1, 3, 6, etc. are growing faster and faster as we continue. Fine. Okay, here's the second example that we had. This geometric series, which the sum of 1 over powers of 2, 1 plus a half plus a quarter plus an eighth, etc. So if we do the same trick there, I take the sum of the first term only and then stop, we get 1. If we take the sum of the first 2 terms, 1 plus a half, we get 3 over 2. Okay, fine. If we take 1 plus a half plus a quarter, then we've got 4 quarters plus 2 quarters plus 1 quarter, so we got 7 over 4. If we add on to that the next one, which is 1/8, we get 14 over 8 plus 1 over 8, so we get 15 over 8. Then we add on 1/16, we get 31 over 16, and so on. So these are these numbers. It's written in the left-hand side of that line what they are, but in case you're looking at this later and you're wondering what are they, they're the partial sums. Okay, the first thing in this list is just the first term. Second thing in this list is the sum of the first 2 terms in the series, and so on. And here, looking at those numbers, even if we're just looking at it in a kind of casual way, we can see, oh yeah, they're not flying off to infinity like the last ones were. They're actually sort of seem to be kind of behaving in a kind of controlled way. And we've got 3 over 2, 7 over 4, that's nearly 2. It's just 1 quarter short of 2. 15 over 8 is nearly 2. It's just 1/8 short of 2. 31 over 16, it's just 1/16 short of 2, and so on. And we can see the next one is going to have 64 as its denominator, and its numerator is going to be just 1 less than 128. So it's going to be 127 over 64. So here we can see that the sequence of partial sums has a kind of more controlled behavior. We haven't proved anything yet, but we will shortly. But we can observe that, yeah, these numbers are, there's a pattern here. We can see what it is. And we can notice that the terms added on at each step are shrinking towards 0 as n increases. And the numbers in the list marked in red here seem to be converging to 2. Okay, so this looks like a sequence that is converging to 2. And we know what that means in a precise way for a sequence. So we might say, well, okay, well then, as we keep adding on more and more terms in this sum, the running total is converging to 2. That's essentially what we're saying. And that would be what we would mean by saying that the series is converging to 2, or that the sum of those infinitely many numbers is actually equal to 2. So that's an example of what we'll soon be calling a convergent infinite series, and its limit, or its sum, is 2. Okay, the harmonic series, and we had a look at this earlier in our introduction to chapter 3, and what happens here when you start writing down some of the partial sums, I've just written down the first 4 of them, 5 of them actually, is so the fifth one here is 1 plus a half plus a third plus a quarter plus a fifth. Yeah, it's nothing kind of, I suppose, strikingly obvious here in terms of a pattern. Of course, like the denominator in the fifth term here is going to have to be the least common multiple of 2, 3, 4, and 5, which is 60. And so it's not a very neat, very visible pattern like the previous example. And maybe we can't really guess from glancing at that what's happening in the long term. Okay, so it is true that when you sum up the numbers 1 over n, the term that you're adding on at each step is shrinking towards 0. So potentially this thing might not be this running total might not be going towards infinity, but it might be. We don't know yet, but we'll know in a few minutes. Okay, so the harmonic series, from a casual glance like this at it, it's not easy to see what's happening. Okay, and then the fourth example that we had there today, we mentioned this already, but if you take the alternating series whose terms alternate between 1 and -1, starting with 1, and when you look at the running totals there, you start with 1, then you add -1, then 1, then -1, and so on. So the running total just alternates between 1 and 0. And certainly, if you look at the terms of the sequence 1, 0, 1, 0, 1, 0, that's not a convergent sequence. We've looked at that already in the last couple of lectures. Okay, it doesn't have a limit with the property that if you proceed out far enough, the terms are all clustered closely around that limit. Okay, so this is an example of a series that we would call divergent. Its sum is sort of bounded, I suppose, because it's just alternating between 0 and 1, but it's not. We can't give it it just continues to oscillate like that. It doesn't have a limit. Okay. So yeah, I think we said all this, but the lingo here, the series in the second example converges to 2. The series in 1 and 4 are both divergent. 1 was the sum of all the natural numbers. 4 was this alternating one. And we can't really say a whole lot about 3 yet, but we'll know shortly that it's also divergent. So we're going to give precise meanings to these terms now for series. We have them for sequences already. And really all we're going to do is translate what we have for sequences into series using the device of the sequence of partial sums. Okay, does anybody have a comment or a question at this point? Okay, if not, then let's move on. So here's a bit of, I suppose, kind of technical machinery, but we said all of this already for the examples. So if you find it helpful to kind of move between this formal definition and the examples, that might be useful. So let's suppose that we have a series, an infinite series. The terms are an, we're starting at 1 instead of 0 as in previous examples, it doesn't really matter. And okay, so this is an infinite series, and we're taking it that its terms are numbers, and maybe we know what they are. Okay, so for any k from 1 onwards, or from wherever your n starts onwards, we can define a new animal, sk. Okay, and so for each k greater than or equal to 1, we're defining sk to be the sum of the first k terms in the series. Okay, so sk is a1 plus a2 plus a3 up as far as ak. So s1 is just a1, s2 is a1 plus a2, and so on. And you know, these are numbers. They're just sums of a finite collection of numbers. So they're certainly a perfectly they're not just formal expressions. They are numbers. Okay, for any finite sub collection, we can add them up and get and see what the sum is. Okay, so the SKs are numbers. They're not just formal sums. Yeah. Okay, and they're called the partial sums of the series. Okay, and SK in particular is called the kth partial sum of the series. Okay. And then the sequence of all the SKs, that should be round brackets, not a curly ones, sorry, that's because they're in order. The sequence of all the SKs is called the sequence of partial sums of the series. So basically, you can think of the elements in the terms of the sequence of partial sums as just being running totals if you attempt to calculate the infinite series by adding up all the terms from the first one onwards. Okay, so you have this sort of running total, and those, the running total at each step are the terms of the sequence of partial sums. Okay, so the advantage, I suppose, of kind of expressing this in terms of a sequence of partial sums is that we have a theory of convergence for sequences. We know what it means for a sequence to converge. Okay, it means that the sequence has a limit, and we have a very precise meaning of what that means in terms of how the terms of the sequence approach the limit, and how they, and how it's possible to, if the terms of a sequence approach a limit, L, let's say, remember that means that no matter how small of a sleeve we take around L, we can reach a stage beyond which all the terms of the sequence are within that narrow band. Okay, so that's what convergence means for a sequence. Okay, so if the sequence of partial sums converges to a limit, let's say called S, then the series is said to converge, and S is called its sum, or maybe its limit, but its sum would be. Sequence of partial sums converges to a limit. Is that a question? Sorry. Okay, so. And in that situation, you could say that the sum of the series is actually S, and you could refer to the S, the number S, as the sum of the series. And of course, sometimes, as usual, we might have some theoretical machinery that allows us to determine that a sequence is convergent, a series is convergent, without necessarily being able to calculate its sum. But sometimes we can calculate its sum. Okay, so that's the meaning of convergence for series. And I guess this is something that's worth bearing in mind as well. You know, we have a sort of very precise definition of convergence for sequences. The meaning of convergence for a series is that a series is convergent if its sequence of partial sums is convergent. So there we're kind of carrying the machinery that we have from sequences to be able to give a definition for convergence of series. Okay, that's the theoretical kind of heavy lifting for today mostly. A couple of examples. And one example that's important is a geometric series. Important, I suppose, both because we can handle them relatively easily and because they do turn up quite often in various applications. So our second example there earlier was the sum 1 plus a half plus a quarter, etc. And we sort of, by looking at the first few terms of the sequence of partial sums, we observed that it looks like it's converging to 2. And so in this example, just to kind of reframe this in the language of sequences of partial sums, I suppose, in this example for k greater or equal to 0, the partial sum sk would be the sum of the terms from 1 over 2 to the 0 to 1 over 2 to the k. Okay, so that would be 1 plus a half plus a quarter up as far as 1 over 2 to the k. And as it happens, because this expression has quite a nice description, it's a sum of terms, k plus one of them, because there's 1 plus k. And each part of this finite sum is obtained from the previous one by multiplying by a half. And in such cases, rather than having to do the addition by adding the k things together or k plus 1 things together, we can give ourselves a little shortcut by noticing that if we just take the same expression sk and multiply it by 1/2, so in this case, at this stage, maybe the thing to look at is this version of the description. If we take that sk and multiply it by a half, then what, of course, you observe is that you get most of the same terms appearing, except that you lose the 1 because it gets multiplied by a half. You get a half plus a quarter plus an eighth and so on, plus 1 over 2 to the k, plus that one multiplied by a half, which is 1 over 2 to the k plus 1. So basically, you lose the 1 and you add on an extra term at the end if you just multiply the whole thing by 1/2. Okay. And the advantage of that, I mean, I suppose, what am I trying to say? We'd like to have a sort of form for this expression in terms of k that we could just calculate directly in terms of k without having to do a whole lot of addition. And this little trick is a way of accessing that. So if we notice that sk is this first initial piece of a geometric series, multiply that by the common ratio, which is 1/2, and you get a very similar looking expression, except that it's missing the first term and it's got an extra term at the end. And now if we subtract the second equation there from the first one, on the left-hand side, we get sk minus 1/2 sk, which obviously is 1/2 sk. And on the right-hand side, all these terms cancel in the difference, except for the first one, which survives, and minus the last one. So we get that 1/2 sk is 1 minus 1 over 2 to the k plus 1, which is just the difference of these two expressions. And that's telling us that sk, multiplying that by 2, is 2 minus 1 over 2 to the k. So we're saying here that the sequence of partial sums, its sk term is 2 minus 1 over 2 to the k. Okay, so the sum up as far as 1 over 2 to the k is this expression, 2 minus 1 over 2 to the k. We already sort of observed that for the first few terms of the sequence, but we can observe there by looking at what happens to that as k goes to infinity. Well, the 1 over 2k part, 1 over 2 to the k part just goes to 0. So that sequence converges to 2. Those values approach 2 as k increases. And so our conclusion then is that the series converges to 2, and that, yeah, in a very precise sense, the sum of all the fractions of the form 1 over power of 2 is actually equal to 2. Okay, so this is an example in the geometric series where we can actually write down the, a sort of very usable expression for the terms of the sequence of partial sums. Okay, so that would be a rationale for the claim that that series has sum 2, or that the series converges to 2. Okay, so I suppose geometric series are the main examples that we're going to look at in terms of like a family of convergent series. There's certainly a lot more that one could say, but we won't manage to do it in the last lecture or two. Okay, then just a general remark about geometric series in general. So if you have a geometric series, and typically a geometric series will look like this. It'll have a common ratio, R, which is what you multiply by to get from one term to the next, and it will have an initial term, which is the first term, A. And we'll assume that A is not 0 here, because if A is 0, then every term in the series is 0, and it's not such an interesting series. So this is what a geometric series generally looks like. And this is just saying, when n is 0, which is the first term, then the R part is, the R to the 0 is just 1. So the first term is A, second term is AR, then AR squared, then AR cubed, and so on. I don't know, sometimes when you look at this, maybe it's not so, there's a lot of things to see there. So it might not be sort of immediately obvious that it's a geometric series, but that's the general form of a geometric series. And a geometric series is determined by its first term and by its common ratio. As soon as you know those two things, then every term is obtained from the previous one by multiplying by the common ratio. So you know all the terms of the series. Okay, so in our previous example, the initial term was 1 and the common ratio was 1/2. So we got 1 plus a half plus a quarter plus an eighth and so on. So just I suppose the observation here is just that we can do what we did in the last example for any series of this form. And so, if you don't like this sort of abstract description, give yourself a concrete example, give yourself a value for R and for A, and write down the terms and satisfy yourself here that the steps make sense. So, okay, the term that we'll call SK would be the sum from n equals 0 to k. So writing that out from the longhand, that would be A plus AR squared up as far as AR to the k. Okay, so this is exactly what we had in the previous slide, 1 plus a half up as far as 1 over 2 to the k. If, as we did in the last slide, you take that expression, and I think for me, I find it helpful to look at the right-hand side here, the sort of longhand version of it, with the terms written out with plus signs between them, and look at the multiplied by the common ratio. So you've got SK and RSK, and RSK is just AR plus AR squared plus AR cubed up as far as AR to the K, and then plus R times the last term, which is AR to the K plus 1. So the reason for the alignment here, of course, is just that the terms that match each other are aligned. So we're kind of, so instead of writing the AR under the A, I've written it over here. The AR here is this A multiplied by R, and same thing over here. Okay, and the reason for that, of course, is because then the matching terms line up in columns, and you can see how the subtraction works. So if we take SK minus R times SK, that is just doing the subtraction, all these bits cancel, and you're left with A minus A times R to the K plus 1. Okay, that's 1 minus R times SK. Okay, if R is 1, of course, we're in trouble at the next step because we don't want to divide by 0, but if R is 1, all the terms in the series are equal to A anyway, and we can see that the series is divergent in that case. So we're assuming here that R is not 1. And then if it isn't, then we can translate this statement into a formula that tells us how the term SK of the sequence of partial sums depends on K. It's just A, the initial term, times 1 minus this power of R to the K plus 1 over 1 minus R. Okay. And if R is less than 1 in absolute value, then this bit, this R to the K plus 1, is going to 0 as K increases. Just high powers of something that's between 0 and 1 in absolute value, that will head to 0 as we keep taking higher powers. Okay, so in a case where the common ratio R is less than 1 in absolute value, then the sequence of partial sums, this is its kth term. And as K goes to infinity, the R to the K plus 1 goes to 0, and the kth term in the sequence of partial sums. And remember what that is. That's the running total as you add together all the terms in the series from the first one onwards. Okay, the running total after you've added up terms as far as the AK term. Okay, so if the absolute value of the common ratio is less than 1, then this sequence of partial sums, and hence the series, converges. And what it converges to is the limit of the terms of the sequence of partial sums as K goes to infinity, and that's just A, the initial term, over 1 minus R, 1 minus the common ratio. In our previous example, the A was 1 and the R was 1/2, so this would be 1 over 1/2, which would be 2, which agrees with what we observed. And if the absolute value of R is greater than 1, then certainly in that case, the R to the K plus 1 is going off to infinity, plus what, maybe alternating between plus and minus infinity, or maybe just, but certainly it's going without bound. So in that case, the series is divergent. If R is equal to 1, that's slightly trickier to read from here. But if R is equal to 1, then the series is just A plus A plus A plus A plus A. So unless A is 0, it's divergent. Okay, so that's the sort of general theory, I suppose, of convergence for geometric series. And basically, whether the series converges or not only depends on whether the common ratio is less than 1 in absolute value or not. And if it is, then you can very quickly write down the sum of the series just from knowledge of the initial term and the common ratio. It's just A over 1 minus R. So really, the world of geometric series is as nice a world as you could be in if you're dealing with infinite sums. Okay, they're the most manageable examples. Does anybody have a question or a comment there? Okay, if not, then that's the only sort of real kind of family of, or sort of class of series that we're going to look at in any detail. But I did promise an answer to the question about the harmonic series. So the harmonic series is the sum of the reciprocals of the natural numbers, 1 plus 1/2 plus 1/3 plus 1/4 and so on. And the assertion is that the harmonic series is divergent. And I claim that we have all the machinery that we need to see this. And actually, this is a little link that we have between our current topics of interest and what we talked about in chapter 1, back when we were talking about integration, which hasn't really appeared since. So we can recall something from section 1.5 in particular to let us see that the harmonic series is divergent. So let me try to draw a picture to try to indicate why we might make this conclusion. So we're talking about the series (1 plus 1/2 plus 1/3 plus 1/4). And okay, there are different ways to show that a series is divergent or convergent. But one thing that we can do with this one is to just imagine what that sum would look like, and to basically envisage a region that would have that sum as its area and compare that to something that we did back in chapter 1. So what we're going to do is draw a picture of the Cartesian plane, or the x-axis at least, with the integers 1, 2, 3, and so on. Natural numbers spaced along it. And so the y-axis is here. There's the point 0, 0. And we're going to represent, so we're going to draw a rectangle of height 1 over n with base being the closed interval from n to n plus 1. And this is for n greater or equal to 1. Okay, so on the interval from 1 to 2 then, we're going to draw a rectangle of height 1, that's a square. Okay. And the area of that rectangle is 1 times 1, so it's 1. And then on the interval from 2 to 3, we're going to draw a rectangle of height 1/2. So this is 1/2. This is quickly going to become a bit of a mess. On the interval from 3 to 4, we're going to draw a rectangle of height 1/3. And on the interval from 4 to 5, we're going to draw a rectangle of height 1/4, and so on. And we keep at it, and then 1/5, and so on. So we can certainly assert the area of a rectangle of base length 1 and height 1 over n is 1 over n, of course. So this first square has an area of 1. This one has an area of 1/2, 1/3, and so on. And 1/4, 1/5. So, you know, this picture extends the whole way along the positive side of the horizontal axis there. And we have all these little rectangles that are shrinking in height, but they all have base length 1. And we're talking about the total area of that whole region that's colored in this orange color. Okay, so fine. We can certainly envisage our infinite sum that way. How does it help us? Well, it helps us maybe because we do have a means of calculating areas of regions, at least sometimes. Okay, and something that we can observe is that if we draw the graph of the function y, or if we draw the graph y equals 1 over x, it passes to the point 1, 1, and it passes to the point 2, 1/2, and the point 3, 1/3, and 4, 1/4, and 5, 1/5, and so on. So these points labeled in red, this is 1, 1, this is 2, 1/2, this is 3, 1/3, and so on. And if you imagine the continuous function f of x equals 1 over x, its graph passes through all those points, and it's a continuous smooth thing. So it looks like this. It's decreasing, strictly decreasing. And so it completely sits below the upper boundary of this orange region. Okay, so this red graph is the curve y equals 1 over x. And if you cast your mind back to section 1.5, when we were talking about improper integrals, we already know that the area enclosed by the graph y equals 1 over x, and the x-axis from 1 to infinity, I suppose, from x equals 1 onwards, that area is infinite. Because we proved back in section 1.5, that the improper integral from 1 to infinity of 1 over x is divergent, that it's the area enclosed by that graph is infinite, the area is accumulated without bound as we proceed to the right. So basically the orange area, okay, how does that tell us that the harmonic series is divergent? Well, the total area of these orange rectangles completely includes the area under that red graph. So the area, the area of the orange rectangles exceeds this infinite area enclosed under that red graph, so it must be infinite as well. So the sum of the harmonic series, or the orange area, exceeds this. So it is also an infinite area. Okay, so that's one way to see that the harmonic series is divergent. It's not the only way, and there are other very nice ways as well, which are detailed in the lecture notes. There's at least one other way, note in the lecture notes explaining how this series is divergent. But one way is to make use of our knowledge about improper integrals and to note that, well, this sum, if it has a value, it would represent that area which exceeds an area of a region that we already know to be infinite, because the orange area there, okay, here's where I'm going to completely make a mess of the picture. The orange area includes all the red area under this curve, plus other bits that are included in the orange part, but not the red part. So certainly, if the red one is infinite, the orange one must be infinite as well. So that tells us that the harmonic series is divergent. And the same argument is basically written in text there on the previous slide. Okay, so a couple of final remarks before we proceed to look at some applications of all this stuff next week. One is that a necessary condition for a series to converge is that, again, sorry, I've got this. This should be, these brackets should be round parentheses, not curly brackets, to indicate we're talking about a sequence. So if a series, an infinite series of sum of all the terms an converges, then certainly that has no chance of happening unless the individual terms in the sequence of the ans converges to zero. If the individual ans that have been added on at each step are not shrinking to zero and then heads to infinity, then there's no possibility for this series to converge, for this sequence of its partial sums to converge, because it's just changing too much at each step. So basically, if somebody asks you whether a series is convergent or not, the first kind of check to do, even subconsciously, is to sort of glance at what the nth term is. And if that's not heading towards zero, as n heads towards infinity, then the series has no chance of converging. Okay, and the example of the harmonic series certainly shows us that the condition that the nth term be approaching zero as n increases to infinity is not sufficient to guarantee that the series will converge. The sum of the series may still blow up to infinity, for example, even if the terms are converging towards zero as n increases. So basically it boils down to a question of how fast they're converging towards zero, and the terms 1 over n of the harmonic series are just not converging towards zero fast enough to keep the infinite sum finite. In the case of 1 over 2 to the n, as we saw, they are converging towards zero much faster and fast enough to keep the area bounded, as you, if you were to draw the corresponding picture there. Okay, so that's essentially what we have to say about infinite series. A few learning outcomes for this section. So I suppose, what would I expect you to be able to do? So I guess explain what an infinite series is, how it's distinct from the concept of an infinite sequence, and what it means for an infinite series to converge. So to be able to give some account of the concept of the sequence of partial sums and the convergent for that. I guess I could expect you to give examples of convergent and divergent infinite series, show that the harmonic series is divergent, maybe using that sort of approach of comparing it to an improper integral that we know to be divergent, and have some familiarity with the sigma notation for sums. Okay, so as I remarked before, what we're going to do next, and our final move in this course will be to have a look at some series representations of functions. So one of the questions, I guess, that we started with was, if you wanted to know the values of some function that you can't calculate directly, like even something very familiar and useful and sort of, important, like the trigonometric function, sine and cosine or something like that, how do you actually calculate the cosine of 2 or the cosine of 3? We know what it means geometrically. It's the x or y coordinate of some point in the unit circle. But if you want to know what it is, like how do you calculate it? And so one way to do it potentially is to represent the function using basically an infinite series. Okay, what that will mean, we will see next Wednesday. Basically, it's an infinite series involving some sort of an argument or variable for the function, and it can often be done. And it's an incredibly useful device that's used much more frequently, even in everyday life, than where it's actually visible. So that's our last thing: it's how to kind of take all this theory that we've developed for convergence of sequences and series, and look at what it means for representing functions, even very familiar functions. So that'll be our final topic next Wednesday. That's what we have for today. So I'm going to stop the recording and thank everybody who has joined us for the recording, and enjoy the long weekend, and see you next week.